Hello, my name is Jason Paul. I'm joined in this presentation by Matthew, Dominic, and Lewis, and this will be our first presentation for our EE327 project that we're titling Rook No Hands. So let's get into it. The product that we are designing is a self-moving chessboard, the concept of which is rather simple, right? It's a chessboard that you can play as normal locally with pieces on a board. But underneath, it supports playing against virtual opponents or an opponent that is far away, as well as the local control aspect of it. So it has magnetic pieces that are moved around with an unseen gantry system that can move the pieces independent of the user. One of the key features of this type of project, this one image here is Phantom, a Kickstarter, is kind of the seamless, robust design. So we're making a lot of the parts in-house and using some specialized techniques to get a really solid product that can, be a fixture on anyone's living room table.
When we were first designing our board, one of the first things we wanted to get out of the way was how we're actually sensing where pieces are in any given time. To do this, we decided to have magnets be in the base of each of our pieces and have a Hall effect sensor under each square of the board in order to detect these. We decided to go with these DRV 5032 FA or FB Hall effect digital switches, as you can see on the right. So we chose these because, one, they're very low power, which means we can have a lot operating at the same time, and we will have the option to go with a battery-powered power source later down the line if we so choose. They're omnipolar, which means they respond to either a north or south pole. This should prevent any confusion due to a misaligned magnet placed in the base of each of our pieces. They're push-pull switches, which means they will be outputting a voltage when energized as opposed to open drain, which will be essentially making a connection to ground. And you may notice I said FA or FB switches. This is because the FA version, which has a higher refresh rate of 20 hertz, is only readily available in through-hole version. The SMD version is more expensive and there are fewer in stock. So if we do choose to go with this, for our boards, we will need to choose the lower refresh rate version. So now how are we actually going to be attaching these underneath our board? We wanted to do something that would be robust and not too complicated, since we have 64 sensors total, and you can get rat's nest fast if you're not careful. So what we decided to do is have this replicable PCB design on the right. You can see our napkin sketch of it. So this will cover a 2x2 grid of the chessboard, 4 sensors each for each of those squares. And you will see that we have our power inputs connected across in each row of the board, and then we have our outputs connected in each column. So these boards will connect to all of the 2x2 grid PCBs beside from them. And then these will all connect back to a coprocessor board, which will have a multiplexer attached to it. So this multiplexer will, so the coprocessor will select which row at any given time is receiving power, which row of sensors that is. And then the GPIOs will be connected to each column of the board. So these will be listening to the outputs. So what's going to happen is we will cycle through each row of the board, which receives power, and then you listen for all of the outputs. So you only get one row at any given time. And then you can compare these to the last value you received, and there, whenever a piece is moved, if that value changes. So this coprocessor will be in communication with the main processor. At its very bare bones, it'll just output a bit stream of 64 bits, just saying which piece on the board is where. But we also hope to offload some operations to this board, since it should just hopefully make things smoother. We might want to asynchronously have it tell where a piece got moved to if a move happens, and then the main board could potentially just check whenever it wants for the state of each square, that as sort of a checkup. So yeah.
So when it comes to design choices of the software, we want to design a firmware that fulfills the below requirements. So first, let me go into motion control. So we want to control the motion system by sending and receiving commands from the ESP32. So so the ESP32, which will control the stepper motors, linear bearings, pulleys, etc. So we aim to do this by using a library, which will be most compatible with our hardware components. Second, we have to go to piece detection. So we want to be able to detect when each piece is kept on the board, which each piece is taken off the board, or each piece is taken off. And we'll aim to do this by using Hall effect sensors and magnets. So this can be used by integrating the sensors using the ESP32 and processing the sensor data to determine the state of each square. So we'll be using a grid system where we'll be going 2x2 squares to go through this. And for the game logic, we will be including rules for legal moves, capturing pieces, and when the situation is checkmate, we'll be implying the following conditions to be onto the firmware to indicate that the player has lost or won. And this we will mostly be doing this by implementing a custom game logic by creating a board and mimicking the movements. You preferably using Python, or we can also implement a chess engine, which we will be deciding upon further advancement. Also, from the user interface perspective, we want to provide a user interface that allows the users to interact with the chessboard. So we will be keeping push buttons or LEDs to give feedback to the user, and push buttons to maybe like once the turn is done or reset the board or whatever. And finally, connectivity. So mainly we will have a main server to allow two devices to connect to each other. So we will be using a communication protocol that allows the board to send and receive data from the server. We aim to do this by using an API or a custom communication protocol based on MQTT or some WebSocket API.
As the chessboard essentially needs to move pieces on its own, our chosen method is to do that with an electromagnet, which moves under the board, picking up the chess pieces and moving them to their correct location, corresponding to the other player's location on their board. So we are then using a gantry to provide the precise mechanism needed to move these chess pieces. So an H-style gantry system was chosen because of the symmetry of this design and its its easiness to be able to CAD each of the components in Onshape. Virtually because of the limited budget, we need to manufacture a lot of the parts ourselves, which will require a lot of CADing, and it is best to choose a design in which we can CAD everything quite easily. So we'll be using 2 stepper motors, which is the minimum number of stepper motors that's required to drive an XY sort of gantry system. And each of them will require a driver board, which we will pair with a pre-built CNC gantry coding library to basically be able to just send G code commands so that the gantry will be able to essentially move quite easily, and we don't have to worry about complicating our firmware too much. So a lot of the parts we will have to manufacture ourselves, which will include the end holders, the rods for the gantry movements, the linear ball bearings, and essentially the moving blocks or the moving components, which will house the linear ball bearings and which will carry the electromagnet around. So all of this gantry system will be essentially hidden inside our chessboard, which will be built around the gantry and the electronics and the PCB, so that all of this is hidden so that the end user will not be able to see any of the components around, but the electromagnet will still be able to essentially move the pieces, as we'll try to build the gantry system holding the electromagnet very close to the actual PCBs and the chess pieces, so that it will be able to efficiently pick up the pieces and precisely drop them to where they need to be delivered.
So a couple of the constraints for this project involved cost. So a lot of pre-built gantry systems are quite expensive or utilize a lot of specialized machined parts. The good thing is that I have 5 years of machining experience under my belt, so I can manufacture many of these parts ourselves. So the plan is to go with majority machined aluminum parts, end blocks, and the actual carriers for the bearings and guide systems for rigidity and also for the lightweight properties of the material. And then machining some steel bearing guides. So we'll have steel bearing guides with linear ball bearings with a Delrin sleeve running across the length of the gantry in the X and Y direction. Since we don't have any Z height to worry about, or Z motion to worry about, we can constrain ourselves to those two bearing guides and then manufacture some linear ball bearings to help ease the friction of the movement of the gantry for the steppers. For gearing and belting, we're going to purchase that off the shelf just to make sure that we have everything compatible across our steppers belt system, as well as all the pulleys that we select for this particular design. Skipping ahead again.
All right, so here, as you can see, we have our Gantt chart. This is going to be pretty straightforward as of right now. We have most of our high-level ideas laid out, as well as all of the major milestones. So as you can see right now, we are in the midst of our prototyping phase. We're still waiting on our parts to come in, obviously. But once we do get those in, we're going to make a small-scale version of our Hall effect sensor grid. We're going to start working on our gantry, getting our pieces assembled. And then once we can confirm that our prototypes are working, we're going to start working on PCB design, getting more of our stuff integrated, working on the actual encasing, and move from there. Oh, I should also note that we want to get our initial schemes for firmware laid out very soon, which will include the files and functions that we want to include on each device.
In this stage of the project, this bill of materials is basically a draft for what we believe is necessary to build our chessboard. As you can notice, the total unit price is quite high and a little bit over the budget. However, we haven't ordered all the parts yet on this list because we need to essentially do some prototyping first with the through-hole components. So our bill of materials will hopefully update later to have a little bit of a reduction in price, with only ordering the essential components that we need. The higher costing components, as you can see, are basically these Hall sensors, where we will need one for every square. And since there's 64 squares on a chessboard, this drives the cost of getting each individual Hall sensor quite high. And then all the parts that are needed to build the gantry, because it is such a heavy hardware-based part, requires just a lot of cost in that, and each of the components end up costing about $10 each, which essentially drive the price up to what you see. But hopefully we'll be able to drop the cost by manufacturing our own parts and doing some initial prototyping.
So the target population for a proposed chessboard may vary from chess enthusiasts to casual players who are seeking a very new gaming experience, because a board does offer that, tech-savvy individuals and chess instructors. So chess instructors who cannot be in person maybe can use our board to give a very new and innovative learning experience to their students, and also all sorts of board collectors who collect different types of chess boards. So if anybody who's willing to experience a new and innovative way of playing chess and play with your friends or your family across the world, and with this product comes with innovation, and there's a lot of thought and creativity that goes into the project, so it might generally it will impress anybody who's interested in chess. So looking at market trends, the global online chess instruction play market size was valued at 151.94 million in 2021 and is expected at a CAGR of 13.13%, and it will approximately reach around 318 million by 2027. So because this is the online chess market trend, which I just mentioned, so looking at the growing fields, our product will definitely be very valuable in the upcoming years. And also the smart chessboard market size is estimated to be around 45 million in 2020. So the market is expected to continue growing at an annual growth rate of around 10%, and up to 2026 we can expect around 75 million in 2026. So which is a very good going by market trends. Our product will be very desirable in the upcoming years. So we have quite a few competitors who are very similar to what we're making. So I would like to talk about Phantom first. So they have created a very innovative chessboard, definitely, and they have a sophisticated sensor array that detects the precise location of every piece. So they also have a chess engine, so you can also play against a board called Maya, a human-like neural network chess engine. She can, you can play against her. She can level up, and she also uh, can mimic human movements, and is actually a very good opponent. And also it has voice control commands. So if you're too lazy to move the coins, you can just use voice commands to move the chess pieces, which is really innovative. And secondly, I would like to talk about Square Off. Square Off is a smart chess board that uses a combination of robotics and AI technology, which allows players to play against each other online and also has a built-in chess engine. It has a very aesthetic looking board, and the pieces move automatically in response to a player, which is going to put our chessboard in competition, like for competition. But yes, that's Square Off is very good. Like it's really innovative. And the third is the autonomous chessboard, which is a project which we saw in which we kind of took inspiration from. So the board is hooked to a computer and requires the player to input. So like it follows like a grid system. So the player has to input a square address of each piece to be moved to its new location. So again, it also uses an electromagnet, which is moved by two stepper motors and timing belts. And each piece also has a loose steel ball bearing inside to allow them to easily slide around. So I feel these three boards would be potential competitors for our chessboard. So I had interviewed one of my roommates who's a computer science major and he plays a lot of chess. So we had I pitched my design idea to them, and they had given a few recommendations and also their feedback. So first, they wanted us to have some kind of indicator which can indicate whose turn it is. Like sometimes you're just distracted with like some other work or you get a phone call, and so some kind of indicator, some kind of tracking system which keeps in track whose turn is it. They recommended that would be nice. And they also wanted to make sure the response time in the server is fast enough. So let's say someone across is making one board, the player on one board is making a move, and that is sent as a command to the server. And if the server takes too long to respond, that might be a hindrance while playing, and that might also be a little irritating for the users. So they want to make sure that that is in place as well. And another one is LED display. They wanted to keep a count of how many times a player wins, and also a display message on the board if like player one is one or player two is one. And also in case a user took too long, they want some kind of reminder or a clock which shows that the user does not have more time to make a move, or if they are beginners or if they're amateurs or experts, whatever, for like different game modes, maybe they suggested that we could have different game modes to help users play and experience the game better. And from a feedback perspective, they just wanted to make sure, they just recommended that the two pieces do not collide with each other, because we'll be using an electromagnet through a head-style gantry system. So if the one of the major concerns was the pieces not colliding with each other, and also since so many components are moving when we move one particular coin, they also wanted to ensure that there's not a lot of noise made when we're moving a piece using the electromagnet. There are stepper motors and various other components, so they wanted to make sure that the noise is kept to a minimum.
All right, so for our second interview, we decided to focus more on someone who has experience playing chess, get some feedback from them, see what they think of our board. So for this, I interviewed one of my friends who is an avid chess player, showed him a bit of our design, and then asked him some questions about what he feels the user experience should be. So a few features he found that could be useful to add include an LED to indicate whose move it is. It can already be a pain when you're playing chess if you forget whose move it is in person. So if you're trying to play a game remotely, somehow it'll become even more complicated. So an LED will clear things up a lot and make it easier for the player, a lot easier on the players. We should also clearly label each position on the board so this will be pretty straightforward to do with our enclosure. But it should, if as long as we will need to match this up with what each position is in our software. So this should hopefully make debugging a lot easier for us as well. He also emphasized that the board should not be an obstacle to playing the game. If the automated nature of the board is interfering with the player's ability to concentrate, then we have ended up making a product. We have ended up hurting the user experience, and our product is not effective in that case. And lastly, we asked about a chess clock, since this was something that we were considering implementing. And his advice was that it could be cool, but is largely unnecessary, since you can basically just have an app on your phone do that on the side, and it'll be just as good. And you can even probably control it to finer degrees than we could integrate. So while it would be nice, it's not necessarily important. Since my friend is also an engineer and he has a design experience, we were able to get some feedback in regards to a few aspects. So one of the biggest one of these that we heard back from was in regards to the electromagnet that's actually going to be moving our pieces around. He emphasized that like one of the biggest problems he saw potentially is that the pieces might not be far apart enough to avoid interfering with each other or getting attracted to the magnet. So we'll need to make sure that they're spaced properly when we do our testing with the magnetic sensing grid prototype and the electromagnet. If these pieces are just barely not far apart enough, then it might be useful to also add a bit of a weight to each of the pieces. This should basically make them just a bit less sensitive to interference.
So one, it was an interview, but a new thing that we have learned was from Bob Taglia, one of the tool and die makers in the Siegel design shop, who I've worked closely with for a number of years. We discussed a little bit about how to manufacture linear bearings. Typically, they're quite easy to manufacture given the right equipment and tolerances. So simply just a precision bore with a Delrin sleeve, Delrin being a bearing plastic it's self-lubricating and can withstand wear quite easily with a relief cut out of it for a press fit, and then bearing races, so channels cut into the plastic to constrain the bearings from basically rolling all around the sleeve, and then a steel shaft, which is used to for the bearing to ride along. Steel is required here for the wear characteristics. Alumina would simply deform too easily under the stresses involved. So should be pretty doable with the tools that we have at hand, and we're excited for the challenge to manufacture these in-house. Diameter tolerances are going to be the most critical, right? We have a lot of precision shafts that need to be machined to dimension and then fit to dimension to specific bearing sizes that we're creating, as well as, you know, the ball bearing, the tolerance of the ball bearings themselves. The biggest issue that we foresee here is going to be run out on the machines that we have available. So run out being deflection of a shaft as you machine it to diameter across the length of a part. So, for example, bad run out would be the variance in diameter across the surface of a part. Typically, we're looking for run out and diameter tolerances within a couple thousandths of an inch in order to achieve good motion without the bearing binding on the shaft, which may be a challenge with the machines that we have on hand. So Bob and I will work together very closely to try and resolve these issues and see what we can do. But we're confident that we're going to be able to put together something that works for us here.
Our first question that we would like to ask you is about our hardware design. So as we are currently in the process of designing the H-style gantry, we are looking for design input. If you are familiar with gantry design, we're asking if you have some suggestions for the design of our H-style gantry or any advice from previous experience that might help in creating our gantry and manufacturing it. And if you're not familiar, then you're asking for your input on possible hardware design specifications. So these would sort of center around the enclosure, the chest design, the chest piece design, and the board design, and how we should approach it or think about approaching it differently in a way that we might not have thought about before, and some suggestions on what you might believe you might want to see the chessboard have.
One of our biggest gray areas when it comes to designing our sensing subsystem is how to handle communications over serial with our main board in order to report the chessboard state. While we do have a lot of freedom here, this can be paralyzing in some respects. If you have experience setting up communications protocols between processors, what are some suggestions you can offer to us given our project? We're open to any ideas that you may have.
Thank you for watching, and we look forward to hearing your feedback.